Okay, hello everyone and welcome to our May 2021 AGU Geohealth Early Career webinar titled From Paris to California, Co-Benefits of Emission Reduction, featuring our guest speaker, Pascal Polonik, a PhD student in University of California, San Diego. Before introducing our speaker, I would like to go through some housekeeping items. I am Beruz Talab, and I am here on behalf of Geohealth Early Career Committee, and I am your host for today's webinar. So the format of today's webinar is that our speaker will talk about his research about 40 minutes, and then we will have a moderated Q&A session. By default, your audio and video is turned off, and we ask you to please keep them turned off so we can keep the quality high. And in order to ask your questions, you can try and find the participant name Ask Questions here in the participant list and write your questions there, and our team will compile them and I will ask them after the presentation. And just to let you know that this webinar is being recorded and will be posted online, hopefully very soon. So in order to introduce our speaker, it is my pleasure to introduce Pascal Polonik as today's speaker. Pascal did his bachelor's in environmental sciences and atmospheric sciences in UC Berkeley. And then he went to Germany to do his master in meteorology in Ludwig Maximilian University of Munich. And currently he's a PhD student in climate science program at UC San Diego. Pascal's research is primarily focused on climate change and its health impacts. And he's also interested in environmental injustice topics. And actually, he presented his work on environmental injustice in California in AGU 2020 fall meeting, and received the Outstanding Student Presentation Award in Geohealth section. With that, I would like to congratulate again for your achievement, Pascal, and pass the mic to you after stop being my screen.
Great, thanks Beruz. Thanks for organizing this. Let me just get set up here. Okay, I think you should be able to see that. Let me just get a pointer here. Great. So yeah, thanks for that. My name is Pascal. I'm a grad student at Scripps Institution of Oceanography at UC San Diego. And so I'm presenting work today on two separate projects, one about the Paris Agreement and one about environmental injustice in California. And all this work was done with professors Kate Rickey and Jen Burney, who are also at Scripps and at the School of Global Policy and Strategy at UC San Diego, among other people who I'll mention along the way. Okay, so I'm going to jump into part one, which is, like I said, about the Paris Agreement. So most of you probably know what the Paris Agreement is, but just in case you don't, it's this UN climate agreement, which was signed in April 2016, which aims to limit global climate change to 1.5 to 2 degrees Celsius. And the way that they aim to do that is by having each country submit a nationally determined contribution, or NDC for short. And the way that those documents work is that they're fairly unstructured. Each country kind of decides how to describe their context of their country, how they're thinking about this goal of limiting climate change, and then hopefully stating what they actually plan to do to contribute to the solution. So I like this example from Japan because they really lay out the context of this, of how their energy system is changing, about the Fukushima Daiichi nuclear power disaster and how that's rebuilding their energy system. And then there's sort of the magic line here for us, which is that they're planning to reduce their greenhouse gas emissions by 26% by fiscal year 2030 compared to fiscal year 2013. And so that's useful both because, well, mostly because it helps us quantify what the actual changes, what the pledges mean for the future. We can quantify what those greenhouse gas emission reductions imply for the climate. And then just so you know, for context, the US has actually quite a similar goal to Japan, which is a 26 to 28% reduction of greenhouse gas emissions below 2005 levels by 2025. And you may have seen this in the news recently. The US actually left the Paris Agreement for a while. It's now back in February. And US, China, and other countries are currently working on pledges in terms of updating these NDCs looking forward. But what I'll be talking about is the 2016 version of this agreement. Okay, so this is a global climate agreement that aims to reduce greenhouse gas emissions, but I'll be talking mostly about aerosols. And since this is a Geohealth session, I assume most people know what aerosols are, but really briefly, here's a map of their distribution. Aerosols are just small atmospheric particulates that are suspended in the atmosphere. I like this figure from NASA, which shows a few different types of naturally occurring aerosols. So for example, there's pollen here or sea salt here. And these are just tiny little particulates suspended in the atmosphere. So those are natural sources, but there are quite a lot of anthropogenic sources as well, and they're often co-emitted with greenhouse gases. And what that means is that we normally think of burning hydrocarbons, and that creates CO2, water vapor, and energy, which is why we do it in the first place. But in the reality, the fuel that we burn has other stuff in it, sulfur, for example, and there's incomplete combustion. And so you end up with things like carbonaceous aerosols and SO2, which forms sulfate aerosol. So these aerosols are emitted along with greenhouse gases. All right, so there's a couple of reasons why we might care about aerosols. From a climate perspective, we care about them because they can warm or cool the planet. So here's a figure from the IPCC where you can see that there's radiative forcing on the y-axis and different types of aerosols on the x-axis. And that just means they have different chemical compositions, and those chemical compositions influence how they impact the climate. So black carbon, for example, has a positive radiative forcing, which means that it has a net warming impact on the planet. And other aerosols, like especially sulfate, but also organic aerosols and nitrates, have a net cooling impact. And in total, those aerosols have a cooling impact. And what that means is that because they're also emitted by humans, anthropogenic emissions, they're actually offsetting part of the warming caused by greenhouse gases. So we're sort of masking some fraction, and the estimates vary, but maybe it's around a third of the anthropogenic warming from greenhouse gases is being masked by aerosols. So it's not a totally negligible fraction. And the other reason that Geohealth people will be familiar with that we care about aerosols is that they're unhealthy, unambiguously unhealthy. So here's a figure from Burnett et al. 2018, which on the x-axis here has PM2.5 concentration, so it's a small particulate matter concentration. And on the y-axis has the hazard ratio, which is like a metric of risk. And what this is showing is that all these different health outcomes, like lower respiratory illness, stroke, lung cancer, et cetera, increase pretty significantly as you have an increased exposure to PM2.5. And this leads to premature mortality of like millions of people a year globally. Okay, so we're thinking about this in the context of the Paris Agreement. And basically the idea is that depending on how you actually implement your greenhouse gas reductions, you're going to have an influence on your aerosol emissions as well. So the question is what are the potential climate and health outcomes from different implementations of the Paris Agreement through aerosols? And then is there a trade-off between air pollution and climate policies? So I'm going to outline our methods here a little bit. And what we do is we start with a gridded emissions data set like this. This is CEDS emissions. This is used as climate model input for the CMIP6 project. So we want to go from emissions to a health outcome and from emissions to a climate outcome so that we can quantify how a change in emissions impacts those outcomes. So for the health outcome, what we do is we take climate model output of surface concentrations of aerosols, and we do some regressions on the country level and say, how does a unit of emissions change your surface concentrations? So then we can translate emissions to surface concentrations, and from there we can use a curve like the one I showed in the previous slide to translate a change in PM 2.5 to a change in premature mortality. And then on the climate side, we use some values from the literature for translating how a unit of emissions from a given area changes the radiative forcing of the planet. Like, what is the radiative impact of a unit of emissions? And then we use this really simplified climate model called FAIR, which does exactly that. It translates radiative forcing into a global temperature change. So then we have a way to go both from emissions to excess mortality and from emissions to temperature change. Okay, so here I just put one map of emissions on the left, but actually there's a map like this for each economic, or for 8 different economic sectors. So what I'm showing here is a sum of all 8, but there are 8 economic sectors, and what we do is we look at each sector individually and we aggregate by country so that we have these emissions and metrics for each country and for each of the available economic sectors. All right, so what happens when we do that? We can show here some of the initial results that on the left is aerosol forcing per greenhouse gas emission. So if you look, for example, at India here, so the y-axis is just different countries. So India here, you'll notice this fat green bar, which is the energy sector. And the width of that bar is telling you how much, what fraction of greenhouse gas emissions are emitted by that sector. So you can see that maybe roughly 40% of India's greenhouse gas emissions are from the energy sector. And the fact that there's like a large negative value here means that the aerosols emitted by the energy sector are causing a negative radiative forcing, which means a cooling. So the greenhouse gas emissions from India's energy sector are sort of being partially offset by the aerosol impact, like the cooling impact of the aerosols. And then conversely, you have the residential commercial sector here that has a positive value. So that's black carbon emissions that are being co-emitted with the residential commercial, or with the greenhouse gas emissions. And that's sort of causing an additional warming from the aerosols on top of the greenhouse gas emissions from that sector. Okay, and then on the right is the similar figure, but now for aerosol pollution and per greenhouse gas emission. And what that's showing is all positive values, of course, because you can't have negative concentrations. So all the health outcomes are negative. And basically, I think the point of this figure is just to demonstrate that there's a lot of variety between countries and between economic sectors. And when you add all the sectors up and show this on a map, this sort of get the expected result of largest forcing and PM 2.5 impacts in Southeast Asia, but also other industrialized nations, and to a lesser extent, but to a non-negligible extent, in other countries around the world. So what we want to do with this now is think about how we can use these values to sort of think about decision-making priorities at the country level. So what we do is we take this idealized, well, we take each country and do this, apply this methodology, but here I'm just showing an idealized country just to demonstrate what we're doing. This represents the greenhouse gas emissions from a country, and it has 8 economic sectors. And the width of each of these columns shows, again, how much greenhouse gas is being emitted by that sector. So for example, if sector 3 was the energy sector, then in this particular country, you might have 25% of greenhouse gas emissions from the energy sector. And sort of the simplest way to change for this country to change its emissions, if it, let's say it has an emissions reduction goal of 40%. So the simplest and maybe politically most feasible way of doing this would be to remove 40% of emissions from every economic sector, right? So you say everyone has to take the same actions, and you reduce the emissions for 40% for each sector, shown in these brackets down here, and that reduces the total by 40%. But not only are you reducing the greenhouse gas emissions, sort of simultaneously, you're also reducing the aerosol emissions. So you're having some aerosol temperature and health outcomes from those emission reductions. But a different, more targeted way of maybe removing those same amount of emissions that you pledged to remove under the Paris Agreement is through this climate priority. So here we sort these economic sectors by their impact on their impact on radiative forcing, right? So now what we're saying is we're going to reduce all of our emissions from those sectors that are causing the most warming, not just in greenhouse gases, but also in terms of aerosols. So now we're removing all the emissions from sector 3, all the emissions from sector 7, and part of the emissions from sector 5, and leaving the others alone. So this is sort of like the biggest bang for your buck. How can we reduce temperature the most? We're going to, or reduce temperature change the most. We're going to eliminate the greenhouse gas emissions we said we were going to reduce and target those warming aerosols. And then lastly, the same thing again for the air quality priority. So now we're removing all the emissions from those economic sectors that cause the most local air pollution. So we say, yeah, we want to implement our Paris Agreement target, but also we want to clean up our air. And so we're going to target those sectors that have the strongest impact. So here we're reducing all of the emissions from sector 2 and 8, and a lot of the emissions from sector 3. And so, of course, this is not the most realistic implementation, because obviously you can't actually do this in real life, reduce all the emissions from some sectors and leave others alone. But it gives us a bounding scenario of how much these decisions might matter for the aerosol impacts under the Paris Agreement. Okay. So we do this for every country, or at least every country that has a specific pledge under the Paris Agreement. And then we add it up and see what the global impact is. So here's a time series of global temperature change. So from 2020 to 2030, which is the time period during which we sort of artificially implement these changes. And in the gray line is the unmodified case. So this is just making no changes. This is sort of a like baseline scenario. And then the dashed lines are when we make only changes to the greenhouse gas emissions. So this is not looking at the aerosol impact. This is just the impact of the Paris Agreement greenhouse gas emissions reductions. And then the colored solid lines are the priorities implemented as I showed in the previous slide. So what you notice is that the climate priority in red here at the bottom has the least temperature change. And that's like by design, right? We reduce the most warming aerosols. And so therefore you're getting the most, sort of the biggest temperature impact. And one thing to note here is that the difference between the gray line and the dashed lines is similarly large to the difference between the different solid lines. And our conclusion from that is that the short-term temperature impacts of aerosols can be similarly large as those from greenhouse gases. And of course, like in the long term, what we care about is greenhouse gas reduction. Of course, those still have a huge impact. I'm not trying to dispute that. But if you're worried about short-term, like peak warming or something like that, then these short-term impacts can be quite substantial and similarly large to those from greenhouse gases. Okay, and here's the same figure now for premature deaths. So again, between 2020 and 2030, the gray is the baseline case where there's actually an increase in premature mortality over time. And the colored lines are those three priorities. And now the air quality priority shows the most reduction. Again, this is the expected result because we're optimizing to sort of reduce those emissions as much as possible. But the difference is quite substantial. So it's over 1 million deaths a year difference in the next decade. And so depending on your implementation, you get a very different mortality outcome. And the last thing I want to note here is that the blue line, the equal by sector, which is sort of the simplest and maybe what you would expect to be sort of the average of the other two, doesn't actually have the benefit that you could get from optimizing in either of these other two cases. So, okay, so here is similar information as the previous slide, but now it's broken up by region. The x-axis is now contribution to global temperature change, and the y-axis is premature deaths. And each color is a region. So if you look at Africa here, the different symbols are the three different priorities I've been talking about. And air quality priority has the fewest deaths, climate priority has the least temperature change, and the equal sector priority here is, in the case of Africa, sort of objectively worse than the other two, which I think is interesting. So you have sort of more warming and more deaths from this priority, even though it maybe seems like the simplest case. There's other regions where that's not the case. So if you look at North America here, for example, the equal priority, equal by sector priority is sort of in between the other two, and it's not obviously better or worse. It's closer to being an average of the other two. And then lastly, here is the slope between these two extremes, but for every country instead of every region. And so this tells you something about the trade-off between sort of the extreme case where you're optimizing for health and the extreme case where you're optimizing for climate. And the main takeaway for me here is that this varies by orders of magnitude for different countries. And that sort of implies that different countries are going to be thinking about this question in very different ways. All right, so my conclusion from this section are that the ambiguity is, there's quite a bit of ambiguity introduced from temperature, for both temperature and mortality impacts when not considering aerosols as part of the implementation of greenhouse gas reduction targets. That the trade-offs vary by orders of magnitude for different countries, and that the simplest implementation can actually be worse. And so that's sort of an argument for explicitly considering aerosols as part of these policies. Okay, this is the part where I'm gonna take a pretty hard pivot into the second project. So this is what I presented at AGU. I'm sorry if you've heard it already. And this work was done with a whole group of other people listed here. They deserve a lot of credit for what I'll be showing. This paper is currently in review, and so this is still work in progress, something I should also note. So here is a picture of a highway by UC San Diego, which taken a few days after the coronavirus shutdown began, and it really shows how empty things were. And we've conducted this project during this time. So it was great to communicate with these people as I went through, and they were super interdisciplinary and super helpful, and I just really want to acknowledge them for this work. Okay, so we're still thinking about aerosols now, but now we're thinking about it in the context of the coronavirus pandemic. So there were a lot of headlines early in the pandemic. For example, this one, coronavirus pandemic leading to huge drop in air pollution, and the headline described it as the largest scale experiment ever. And of course, this is going to pique some interest for scientists. These headlines started popping up all over the place about China's air quality improving, about Italy's air quality, Europe in general, the US air quality, the Bay Area, LA, so it was all over the place. And atmospheric scientists sort of started to jump on this, and there's been a lot of work done about different chemistry impacts or transport impacts of these changes, but we took a slightly different spin on it, and then we were thinking about what this might teach us about environmental justice. So I also just want to say that I'm new to this topic, at least academically, but I want to frame how we've been thinking about this question. And I'll start with this EPA definition of environmental justice. So environmental justice is the fair treatment and meaningful involvement of all people, regardless of race, color, national origin, or income, with respect to the development, implementation, and enforcement of environmental laws, regulations, and policies. This is a nice definition. It's obviously very broad. It's hard to quantify. There's a lot of different aspects of this that are social and not just physical. So that's one of the reasons that we thought more specifically about environmental racism. So we frame this as environmental racism does not hinge on the intent of the perpetrator. So actions and policies that promote race-based inequalities are racist, whether or not such an outcome is intended. And another reason to consider this, like I said, is that this is often thought about in terms of pollution control and pollution exposure. And so it's much more quantifiable than more abstract environmental justice. And lastly, environmental policy. Just a brief note here that regulations are the backdrop to changing emissions, which have been declining since the passage of the Clean Air Act in 1970. So any disparities that still exist in this framework of environmental policy. And so injustices are sort of the result of policy failure, or in the unequal exposure are the result of policy failure. Okay, so you may or may not know, California is a large and diverse state. So brief overview of the demographics here. The median income is highest in the San Francisco Bay Area and in the southern coastal area. And so this is LA and San Diego mostly. There's a large share of Hispanic people, especially in the Central Valley, but also in other areas like in parts of LA. There's fairly large Asian populations, especially in the Bay Area and in the LA area. And there are several Black communities, but they are much less easy to identify on a statewide scale here. So there are some in the Bay Area and LA as well. But it's the smallest minority populations of the between the ones shown here. And lastly, I want to say that California has been an epicenter for environmental justice research and advocacy, and that we're just trying to sort of add a piece to this, which is what does the coronavirus shutdown tell us about this topic? So we use measurements from two different sources. The first is the California Air Resources Board stations, which are scattered throughout the state as shown in the map. And these are high quality and expensive sensors. And that's part of the reason why there aren't a whole lot of them throughout the state. And then the other data source we use are these purple air sensors. So these are considered fairly low quality. They're quite cheap. People buy these and put them up outside their house to figure out, just to know what their local air quality is like. The problem from a science perspective is that they're considered lower quality, and it's sort of a citizen science type of data source, but there are quite a lot of them, which can make them pretty beneficial. So you can see, especially in densely populated areas, there are a lot compared to the CARB stations here. There are actually a lot more than are shown on the map now, but we use data that was available back through 2019. But since this network is expanding pretty quickly, there are even more now. Okay, so these are the two data sources, and a quick map just showing that there were changes in air quality at pre and post shutdown. But we'll look at this in more detail. And last note about data that we used is the shutdown itself was experienced very differently, both in space and by demographics. So here's a map of percent of days spent away from home. So that means declines in this metric means that you experience a stronger shutdown, right? And that's all the warm colors. The everything green, yellow, and especially red are sort of areas that had a stronger shutdown. And this is from anonymized cell phone data. So you can see that especially in cities, there were stronger shutdowns than in other parts of the state, but really it varied a lot in different parts of the state. So here's a different representation of the same data, but now as a time series. So time is on the x-axis, and the two lines on each of these plots are for the high and low shares of each of these minority groups. So basically, for the blue line up here, we located the area, the census block groups from this map that had the lowest share of Hispanic population, and plotted those as a time series, the average of those as a time series, and then again for the areas with the most Hispanic population and plotted those as a time series. And what you notice is that the areas with fewer Hispanic people had a much bigger shutdown than those with high shares of Hispanic people. There's kind of this transition period in March, and then you can really see the disparities in April. Here's the same figure for Asian populations, but now it's actually reversed. So areas with high shares of Asian people had a stronger shutdown than other areas. And then the trends are less clear to see for Black populations, again, because there are very few places with high shares of Black people. Okay, so we combine all these different data sources to give some insight into the disproportionate air impacts of air quality during this time. So I'll walk through a quick schematic here to explain the statistical model we used. So yeah, that's showing up. So the simplest way to look at the data would be to just make a cross-sectional scatter plot. So each color here represents a different location. And in this example, PM 2.5 increases as the fraction of Hispanic people increases. And the delta shows the predicted pollution difference as you go from 0 to 100% Hispanic areas. And then a slightly more sophisticated way to do this would be to include other variables in the regression to account for relatively static factors like income or population density. And then we keep going. And if you add, if you do the same analysis, but now allow for time varying factors, like you can account for things like weather or seasons. And then here's where we start to think about the shutdown. And there are two sets of points shown now for each location. And the larger ones are on top, and they're from before the shutdown, and then the smaller ones are below during the shutdown. And in this example, the pollution disparities are reduced dramatically by the shutdown. So now the difference between the two deltas tells us how much disparity is caused by the activity that normally occurs but was not occurring during the shutdown. And then lastly, we can also add mobility data into this model, which varies in space and time, as I just showed. And this allows us to parse the impact of the local and the broader economy. So for example, if the mobility of a certain area does not decline a lot during the shutdown, but the pollution does decline substantially, then we interpret that to mean that the people in that area were not responsible for their own pollution because they're still going about their usual business, but someone else's actions are impacting their environmental quality. Okay, so this is what we do. We put all these variables into a statistical model, and we can see, and then we add a racial variable as well. And so that will tell us about how race is predicting the changes in pollution exposure, even accounting for all these other factors. So these models produce a lot of coefficients, so I'm just going to show a few of the main ones here. And what you see in the x-axis here is the change in PM 2.5, pre and post shutdown, and this is relative to non-Hispanic white people. And the error bars are the 95% confidence intervals, so anything that crosses the 0 line is statistically insignificant. And these first coefficients are for the share of Hispanic people. And so what you can see pretty clearly is that whether or not we use the controls that I just previously described, there's a significant disproportionate decline in pollution during shutdown. And so this is what we're calling environmental racism, right? This is an evidence of environmental racism because there's a disproportionate effect for Hispanic populations. And you might say, well, wait a minute, this is an improvement in air quality during the shutdown. How is this racism? And so let me explain how we're thinking about this. It's that you're decreasing air pollution during the shutdown when you're decreasing the economic activity. So when the only way that you can get that is if during the shutdown, the only way you can get that is if without the shutdown, you're having a disproportionately strong impact on those communities from the economic activity. So actually decreasing during the shutdown demonstrates that there's normally a disproportionately bad impact on those communities. Okay, so we do the same thing for Asian communities, and we get pretty similar results actually if you look at the results with the controls here. And initially we thought this was fairly surprising because Asian communities in California are often thought of quite differently from Hispanic populations in terms of their socioeconomic background and education levels and incomes and so on. But maybe in light of recent events, we shouldn't have found this quite so surprising, because there actually has been a history of racism against Asian populations, and we see that here in this particular analysis. And then lastly, we don't find any effect for Black populations, so they're statistically insignificant results. And we think the reason for that, again, is because if you think back to those maps, that there aren't a lot of areas with very high share of Black populations. And so that doesn't mean that Black people do not experience environmental racism in California. There's literature out there that suggests that they do, but it means that this analysis did not reveal that from the shutdown. Okay. So lastly, I want to talk a little bit about sampling, because I think there's an interesting story here from these two different data sources that we used. So here's a distribution of demographics, or specifically of share Hispanic people and different block groups in California. And the black line, which is sort of covered up by the red line, is the actual state distribution. And the purple line is the block groups where purple air sensors are located. And what you notice pretty quickly is that basically purple air sensors are strongly oversampling areas with fewer Hispanic people. And maybe that's not a surprise. So you'll also notice that the CARB sensors are doing a much better job of sampling this tail. So the CARB were the government sensors, and they're sampling this distribution of Hispanic people much better in the state. So we were wondering, well, we have a lot more purple air sensors, but maybe the government sensors actually do a better job sampling the population. So what happens if we run the same analysis using only a subset of these sensors, right? So what happens if we run this for only the CARB sensors or only the purple air sensors? And so here's what we find. Here are the same coefficients that I was showing previously. On the x-axis is change in PM2.5 concentration, pre and post shutdown relative to non-Hispanic white people. And what you can see is that actually, when we use only the CARB data, there's a insignificant result. So we still see this decrease, but the error bar crosses the zero line, so it's not significant. So this is pretty interesting, because the CARB sensors we just showed are doing a better job sampling the population, but the purple air sensors are picking up this effect much stronger, which is shown in purple just below it. Okay, so we can do the same thing again for share Asian population, and purple air actually does a fairly good job of sampling these groups. But again, the CARB sensors are not picking up this difference. And same thing for share black, except of course, like I showed before, we don't find any statistically significant results regardless of which sensors we use. And lastly, for median income here, and you can see really well in these distributions that the purple air sensors are sampling richer populations compared to the state as a whole, and the CARB sensors tend to sample poorer areas compared to the state as a whole. And again, the effective income here is insignificant for CARB sensors, and it's significant for purple air. So sort of the interesting takeaway here is sort of how do we envision the future of monitoring environmental racism? So it's important to do your sampling well. We know that from a host of scientific work, right? That it's important to sample the areas that you're interested in. On the other hand, the number of samples also matters quite a lot, which is exactly what we're showing here. And then in addition, there's this complication of private versus public data. So the purple layer data is run by a private company. So the data is all publicly available, but it's controlled by this private entity. And the CARB data is collected by and made available from the government. And so it continues to be available, yet we find that it actually makes it harder to find these disparities if we don't use the purple layer data. Okay, so quick conclusions here is that historical environmental policy has yielded environmental racism. And we draw this conclusion because, like I said early on, there's a long history of environmental policy being enacted in California that have actually reduced the total pollution exposure of everybody. But it hasn't really done its job in making sure that this pollution is equitable, right? Is equally distributed among different populations. Okay, next, the monitoring could be improved by increasing the number of sensors. So I dwelled on that for quite a while. I think I showed that pretty clearly. And this is a point that I didn't dwell on for particularly long, but the disparities in Hispanic communities in particular are due to the broader economy and not local activities. So that's because we controlled for mobility in this model, and the relatively small, despite a relatively small decline in mobility, they experienced a very strong decline in air pollution. So our conclusion there is that this must be caused by activity sort of in the broader community. And then lastly, more broadly, also thinking back to the first half of this, is that the consideration of aerosols as part of climate policy can have considerable co-benefits, and that whether that's in terms of global temperature change, in terms of global health and premature mortality, or even just environmental racism in the state of California. So with that, thank you very much for listening, and I'm happy to take any questions.
Thank you very much for your nice presentation, Pascal. I mean, in the beginning, it seemed that these are two different topics, but they were really related to each other, as you mentioned in your conclusion here, that if we have environmental injustice right now, then in our climate policies, it will become a problem in the future. So I would like to ask our audience to put their questions in the chat so we could ask them. And I have some questions here, and I would like to start with my question. First, I saw that in one of your plots, you had data of the policy effects of greenhouse gases for Iran. Was it because I am from Iran, or was it that Iran has big share in that?
Yeah, I just included a random sampling of different countries with different economies. I didn't know that you were from Iran, but I just wanted to include sort of a diversity of countries to show the sort of diversity of aerosol impacts. Yeah, but I mean, we have those values for all the countries. I just wanted to include a random sample for the sake of the presentation.
Okay, so actually my question was that, so you showed like two different sides. One side was only look at the air quality. One side was only look at the greenhouse gas effects. And so I was wondering, what is the actual implementation plan in the IPCC? And I saw, I mean, in some of your slides, you showed that maybe we can reach our goal by going to zero emission from the energy sector. And I don't see that it is feasible in near future. So yeah. I was wondering, what is the current feasible implementation plan?
Right. So the NDCs, so these documents that the countries, put out that state their targets, are often not very specific in how they actually plan to implement. So they talk about sort of the types of things they want to do, and sometimes they talk about what capacity they already have, or the smaller countries might not even have any targets, and they say that they support the goal, but they're not they're not responsible for historical emissions, and so they don't actually state a specific target. So that's sort of why we did this, because it, especially on the aerosol side, so the countries that do have targets for their greenhouse gas emissions, and aerosols are very rarely mentioned in these documents. And so the actual implementation is sort of up to the individual country, right? They just say, this is the overarching goal, and how we do it is going to be up to us. So yeah, no, the scenarios I presented are not particularly realistic. I mean, they're not cost constrained, right? So of course, that's going to be a consideration in actual decision making. The point was more to demonstrate what the potential impacts of aerosols are. So in the extreme case, let's say we cared only about temperature, and then we implemented these agreements, and it was sort of meant to demonstrate that the impact of aerosols can be quite significant, and it could be beneficial to consider them at the same time as considering those greenhouse gas emissions. But yeah, I'm not claiming that that this is a super realistic scenario.
No, you're right. Yeah. Okay. We have a question. We just read it not to miss any point. Great talk. Have you considered tailoring your emissions reductions policy scenarios to the current feasibility of replacement? For example, it is currently much more possible to replace energy production with renewable resources than it is to move away from fossil fuel intensive construction materials like cement or steel. So I guess you kind of answered to that. But
yeah, I kind of answered that. I guess it just takes a very different type of model to do that, right? So in this case, we weren't trying to come up with a plan for how a country should do this. It was more to demonstrate what the potential aerosol effects are. I think you need something much more involved, like an integrated assessment model or something that can include the costs and the feasibility of different technologies. But there are people out there actually coming up with more feasible plans, but they're usually, focused on greenhouse gas emissions. And so that was sort of our take on this, is how do we add this aerosol component to that? Yeah.
okay. And I thought, you do not, you didn't include the combined impacts of those emission sectors together, right? You were doing sector by sector scenario, right? You didn't study the combined impact of emission reductions.
So like the time series of the like global temperature change and things like that are from all of the sectors combined.
Okay.
Of course, some were zeroed out or reduced through the methodology, but it sums all of the available emissions. Yeah.
Okay, I see. Okay, now we have one question for your second part. It says, great talk. Do you know whether the purple areas in neighborhoods that are traditionally not well monitored are there because the residents are concerned about their air quality and personally buying and installing the monitors? Or are there environmental justice or academic organizations that are buying and maintaining the monitors in those underserved areas?
Yeah, I think it's a good question. I don't know the exact answer. I mean, in part, there's areas that have, people aren't completely segregated from each other. So you might have wealthier people who are able to buy purple air sensors within a community that has poorer people, right? So I think that might be one reason that there are some in areas, but it does undersample poorer communities and racially diverse communities. So, the other part of the question was whether there are academic institutions doing this. I don't think there really are. Well, I know there are some people at Scripps who are trying to use purple air sensors, but I think it's more for coastal air quality reasons. I do think that's an interesting direction. And I actually asked someone else who was presenting something about purple air sensors that same question recently. I think there's a lot of potential there because of the low cost element to monitor these communities and help identify these disparities. But as far as I know, the current sensors are only there because, you know, whoever wanted one and knew about this product and had the money to buy one, put one up outside of their home. So there's no like state sponsorship of these sensors yet, as far as I know.
Okay, and I would like to add to that have you considered using the satellite data in your analysis?
Yeah, so we did the same thing with satellite data, with NO2 data from Tropomi, and got pretty consistent results. So we actually have that in a supplement. I don't have any slides for it here, but yeah, I mean, the difficulty there is that some of the spatial, I mean, there's limitations to the spatial resolution and the temporal resolution, right? But you do cover the entire state, which is the benefit. You don't rely on this sort of like selective sampling, right? But we did do that, and the results are at least qualitatively consistent for NO2. Yeah.
And I have one question myself, was that I think you mentioned somewhere in your slides that one of the categories, I guess it was low income people, that they were experiencing more polluted air. And the reason was that they were working during the shutdown, right? They were outside more than the other people. I don't know what category was that. But my question was that, have you considered that that factor in your analysis, that if you are looking at one region, that this region is, the race is Latinos, but you are showing that they are not home during the shutdown, so they will not breathe polluted air during the day. So have you considered these factors in your analysis?
So I guess the short answer is no, not in the analysis, but I think there's always this, I mean, we have like talked about it as a group that, of course, there's always this question of when you're monitoring air quality, you don't necessarily, I mean, we're monitoring it at people's homes, right? And we're assuming that the sensors are representative of a block group and the sort of racial, ethnic composition of that block group, and not, it is true that those people go somewhere else to work and that their actual exposure might be different. But I guess the idea is that those communities where people do spend a lot of their time are impacted differently than other communities where people live. But yeah, I mean, I think that's a persistent question through pollution exposure about, I mean, even questions of indoor versus outdoor air quality, you know, sorry, it's a jet, indoor versus outdoor quality, that you don't ever know exactly what a person is experiencing. So I guess this is as close as we got, is down to the census block group level of people's homes. Yeah, but it's a good point that you never quite know what someone is actually breathing in.
Yeah, and it's hard to consider that factor.
Yeah.
Okay, we have another general questions that how would you like to expand your research, your work, and what are the next research topics you might explore in both topics?
Yeah, that's a good question. I mean, I'm thinking, you know, as a climate science person, I'm also thinking about some of this in very different directions. But there's a lot of, oh yeah, it's such a good question that I've been thinking about a lot as a PhD student. I don't know. I think it's really interesting to think about how policies intentionally or unintentionally influence, people's exposure, or how climate impacts are expected to impact people in underprivileged communities. There's a lot of different directions I'm thinking right now. I don't think I have a great answer for that. I think there was some consideration of looking at more of the dynamical impacts of the aerosols, because right now we have very simple parameterizations to translate those emissions to some outcomes, and there are ways to model that to make it more explicit. But yeah, no great answer to that question.
Okay, thank you very much. So let me share my concluding slides. Okay, thank you very much for your great talk. And I would like to thank our audience for being with us and for listening to our talk. And I would like to remind you of our upcoming webinar. And so this webinar is designed for early career scientists, and it will have professional development topics that we would like to ask our senior scientists to teach us something. And we would like to ask our early career researchers like Pascal to present their work and use this platform as an opportunity. And we just put the email sign up form in the chat. So if you are interested to present your work or to give a professional development topic, please fill the form. And I would like to ask you to also become an AGU member, because while this is, let me see, there is something. Okay, yeah. So these webinars are free actually, and you can become a member and use the great resources on AGU. With that, I would like to thank you again and thank our speaker, and have a great Friday.